Hello, AP Chemistry, and welcome to Enthalpy. So this is section 5.3, and basically this whole section, also a little bit dense, but the whole point of this section is to emphasize what enthalpy is and basically how we get the equation, the working definition that we have for enthalpy. Okay, so your book in section 5.3 starts out by discussing the fact that enthalpy, right, is a combination of heat and work, right, where work is the movement, right, our energy going to move something, whether it be a piston or across a distance or whatever, right? But work is the matter of moving something, okay? Heat, right, has to do more with the transfer of energy, right, and usually resulting in a temperature change, okay? Now, the whole point is that work has to involve movement. So if we get rid of that movement, then enthalpy equals heat, yes? So the key takeaway from this entire section is that enthalpy is equal to heat as long as, right, we are at constant pressure, which is what most of our stuff is, right? Constant volume also is a situation wherein this idea would apply, okay? Mostly, we're talking about this. Now, when we say constant pressure, what we mean is open to the atmosphere. Okay? In that, during a given experiment, right? Let's say it's a B day, right? And we run an experiment and it is open to the atmosphere, right? Meaning it is not inherently sealed, right? Meaning that we're not going to get any pressure changes from the temperature being changed, right? Open to the atmosphere. Over the course of that 2 hours, right, the pressure of the atmosphere is not going to change significantly. Yes, there are variations day to day, right? There are variations over the course of seasons and years, but over the course of our 2-hour window in the lab, the atmospheric pressure doesn't change significantly, right? And that's what we mean by constant pressure, okay? Need to make sure you commit that to memory. When we say constant pressure experiments, we mean open to the atmosphere, and that also, by extension, right, simply means that the atmospheric pressure doesn't change significantly over the course of our reaction, which is why we can say that our reaction is done at constant pressure. And as long as that condition applies, then our enthalpy is synonymous with heat, okay, which gives us our equation Q equals mc delta T, right, where heat is our enthalpy, right, as long as these conditions are met, okay? All right, let's do a practice problem. So this one should be relatively easy because this is kind of like what we did last year, right? And again, units. So if we look here, right, this is a reaction with an enthalpy tied to it, right? There should be a delta here. Delta H, right? So this is the enthalpy of my reaction. This is the heat, negative sign. What does that negative sign mean? Right, heat is released, okay? If it were positive, that would mean heat absorbed, okay? So this process releases 196 kilojoules. Note that this could also be written as kilojoules per mole reaction, which sometimes books will say that, sometimes they won't, right? Your book doesn't tend to say that, but sometimes it does, right? But don't worry, that just means moles as this is written, right? So what this could also say, right, is there are negative 196 kilojoules for every 2 moles of H2O2. Or we could say that there are negative 196 kilojoules for every 2 moles of H2O formed, right? Or negative 196 kilojoules for every 1 mole of O2 formed, right? So per every 2 moles of H2O2 decomposed, per every 2 moles of water formed, per every 1 mole of oxygen formed, okay? So here we want to calculate the quantity of heat released when 5 grams of H2O2 decomposes at constant pressure. So bearing in mind this is moles, step 1, we're going to take our 5 grams of H2O2 and do what? Right, turn it into moles. So we have 32, 34, we're just going to shortcut it, 34 grams of H2O2 per every 1 mole of H2O2. And then finally, we're just going to tie our pieces together, right? We know, based on this reaction, that for every 2 moles of H2O2, we get 196 kilojoules released, okay? Those cancel, right? And if we do our math, right, 5 times this over this, do note that the sign is really, really important, right? because, right, that's going to be part of your answer. If you don't have this negative sign out here, you're going to get the answer wrong. Okay? So then you would multiply, divide, get your answer. Be sure you put a negative in front of it, right? Super important, because that's what tells us that that's the amount of energy released as opposed to the amount of energy absorbed. Yes? Fantastic. All right. Thanks for listening. This is an introduction to enthalpy, and we will spend the rest of the chapter talking about different ways to find or calculate enthalpy. Thanks for listening. Be good, and I'll see you soon. Bye.